now the session is being recorded. So let me share my screen. Okay, can you please confirm whether you can see the slides? Thank you, Dragos, for confirming. It's really good to see you guys after the Easter break. And like now you should be preparing for your exams. So first off, majority of you have got over 70 or first class in your assignment 2, which is brilliant. And you have already performed really well compared to your previous cohort, and I'm really proud of you guys. So you should already have got the marks for the coursework, which is assignment 2 and assignment 1, and like almost 40% of the marks you should have already covered through the coursework itself. But now the most important bit is remaining, which is the 60%, and like that's where you have the written exam. And yes, Dragos, the second assignment marks has been released weeks ago. So check your email or check with school office. So even the feedback are also available. So get in touch with the school office and see what's the issue. But I have already released all the assignment marks and feedback as well. Now, today's revision lecture is more of a snapshot on the important topics that you should definitely study, because that will help you to maximize your marks of the 60% of the written exam. We are not going to cover everything from the whole module, especially it's only 1 hour lecture, right? Like revision. So that being said, today, whatever we are going to cover, keep in mind that I'm mentioning this so that you can definitely go through these topics of the module and do revise them, because in that way you will see a lot of things that are being asked as question in your exam are already covered. And again, see, my wish from you guys is that you get the best marks from this module. So let's move onward with our revision lecture today. Again, welcome to CE305, or as I like to call it, the module on how to build your own compiler, which you have already done with flying colors. And I'm really proud of you guys. But now you have to appear for your written exam to put your theory into test in a way. So what type of question format that you can expect? So the paper consists of 4 questions and you must answer all questions. The questions are almost of equal weight. Now, during the exam, you are permitted to use calculator. So do keep in mind the calculator that is allowed to use in the exam is the Casio ones that are mentioned in the slide in front of you. Another quick thing I would like to point out, if you go to Moodle, you will see there's a section called Revision 2022. So you will be able to access this slide directly from that section. And later, after today's lecture, this session, I will also upload the video as well there, just as reference, so that it can help you to kind of with your revision. Now that you know the format of the question that will be asked during the exam and what is expected from you, or what type of device or calculator you can use, let's move on with quick recap. So let's look at the different compilation stages, right? Now, before we move on, who remembers what are the main parts, or when we talk about compilers, what are the different parts of a compiler, or what are the main phases of compiler? Can you put that in chat? Let's say how many of you still remember or haven't forgotten. Don't be shy. So do reply in the chat, or else I will call someone specifically and ask for this question. Yes, lexer, parser or parsing, semantic analysis, and so again, these are the different phases, right? But if a compiler can be broken into certain big chunks or big parts, how many parts are there in a compiler? Yes, Dragos, there are two. So what are the two? Yes, front end and back end. That is absolutely correct. Now, Andre has already mentioned lexer, parser, semantic analysis. Can someone mention lexer, parser, semantic analysis is part of front end or back end? Yes, front end. Absolutely. So glad to see that some of you do still remember this. Okay, so let's quickly recap through this again, right? So technically a compiler has two specific structures, the front end and the back end. But apart from front end and back end, it also has the linker stage or the linker phase. Now in the front end part, what usually happens that your program source code enters and it goes through the process of lexical analysis. Now, the whole job of the lexical analysis is to create token from the program source code. After the tokens are generated, then it is processed by the parsing phase of the compiler. In the parsing phase, a parse tree or an abstract syntax tree are generated. Now, the abstract syntax tree is then processed by static semantic analysis. In the static semantic analysis, you generate, like actually the compiler generate an annotated syntax tree with additional information that helps the compiler to further process it. Now, the annotated syntax tree is then processed by the optimization phase or optimizer of the compiler to create the optimized tree. From the optimized tree, then it's processed by the code generation, which creates the virtual code. Once the virtual code is created, then the virtual code is sent to the back end of the compiler for further processing. Now in the back end, the virtual code is processed by the code generation phase. The code generation phase then generates the real machine code, which is closer to the hardware of the computing system on which it is being executed. So when the real machine code is generated in the backend, it's then further processed by the optimization phase of the compiler, and the optimized machine code is generated. Now, after the optimized machine code is generated, it is then processed by the linkers phase of the compiler. In the linker phase, what happens, the optimized machine code and other form of object code and library code are all linked together to generate the executable file. And executable file is specifically like hardware specific for this computing system on which it is being executed. So as you can see, through the different phases of the compiler, so the input is the program source code, and the output is finally the executable file, such that the program source code can be executed for a particular computing system itself. Now, again, the general structure of the compiler is more or less like a sequence of translation happens throughout the different phases of the compiler, such that it could filter out the errors. It could also remove or put aside any extraneous information that could be passed as part of the source code, program source code. And in the process, also make the data more conveniently accessible. So the final target is to produce an equivalent optimized program that can be executed by the intended computing machine. Now, let's quickly look at the chat. So Soren has mentioned it does not have to be an executable. It can be a library. Well, when it comes to compiler, right? So the final output is actually an executable version of your program source code. So when you create a library, that's actually part of just the translation. What that means is, let's say sometime you can actually develop libraries using a programming language, right? But that when you generate libraries, it's only using certain parts of the translation of the compiler to create libraries. So again, in essence, when it comes to compilers, the basic concept is that the input is a programming language and the output is some form of executable. Now, keep in mind that libraries are actually used to further like develop executables. So if you are using a programming language to create library that could be used by other developers or by you to develop a program, then the program can be again processed by the compiler or further processed by the compiler to generate the executable. So there are certain distinguishable things that you need to keep in mind. When you create libraries, it do translation, but it doesn't always generate an executable. But the point of a library is that it can help a developer to create more code to create executables for a specific computing machine. Does that make sense? Sorry. Sorry. Okay, great. Thank you for confirming. Okay, now important part of the compiler, especially in the front end, is regular expression and regular grammar. As we all know, that the whole point of this is to, like, when we talk about compilers work on specific languages. Now, languages are defined or formed by production rules, which forms the grammar. So a language is valid if the grammar for the language is like correct or correct for that particular language. Now, grammars consist of different production rules. Production rules could be thought as rules that defines what or how the language should behave. So that being said, let's look at regular expression and regular grammar and regular language. What's the basic definition of them? So a regular expression is a sequence of characters that expresses and specifies a search pattern. Usually, search patterns are used by string searching algorithm for finding and replacing operations on strings for an input validation. Now, in essence, it could be thought as regular expression is the foundation of production rule for grammars. Now, when we talk about a regular language is a language that can be expressed with regular expression or a deterministic or non-deterministic finite automata or state machine. Now, as I've already mentioned, a language is a set of strings which are made up of characters from a specified alphabet or set of symbols. So we have mentioned regular expression, we have mentioned regular language. So based on regular language, we also have regular grammar. Regular grammar, again, is what defines the regular language. Regular grammar can be implemented using finite state systems or finite state automata. Now, keep in mind that not all useful languages can be expressed as regular grammars. That being said, finite state systems and the rules of regular grammar have no memory, as you already know. So they cannot count the number of times a particular symbol has appeared or a state has been entered. So for that, we need like more memory-based systems, right? But that being said, let's look at finite state automation or automata. So a finite state machine or finite state automaton is an abstract machine that can be in exactly one of the finite number of states at any given time. The finite state machine or FSM can change from one state to another in response to some input, whereas the change from one state to another is actually called a transition. Now, you should already be aware of this, as this has been extensively covered during the lectures as well. But if you can recall that in automata theory, a finite state machine can be of two types. It can be either of deterministic finite automata or non-deterministic finite automata. Now, in deterministic finite automata, the main key points that you need to keep in mind is that if each of the transition is uniquely determined by its source state and input symbol. And the other thing that you need to keep in mind for deterministic finite automata or DFA is that the reading and input symbol is required for each state transition. Now, on the other hand, as I have mentioned that you have non-deterministic finite automata or NFA, the NFA does not obey the same restrictions as DFA. But in essence, keep in mind that NFA can have epsilon moves or the transition is actually empty, which is denoted by epsilon sign itself. And in NFA, you can also have states where the transition, like for the same transition, it can go to multiple states. But that does not happen in DFA. Why this is important? Of course, like in exam, you can be asked, okay, what are the differences between DFA and NFA? Or you can also be asked if you can draw DFA and NFA based on regular expression. So you should revise these topics as well. Now let's look at a question that was asked in 2020 exam paper. So let's say if you are given a finite state automata like this, where like the state Q0 is the start and the Q1 is the final state. So as you can see, it has different transitions, right? So Q0 can go to itself as B, or it can also go to Q1 as A through transitions, right? So you might be asked, okay, state a regular expression that validate the same pattern for this finite state automata. If that's the case, again, the solution is here, and you should already know that you can start from the start symbol, and depending on that, you can see what transitions are happening, and that will help you to create the regular expression, right? Now, again, you might also be asked, okay, can you convert the regular expression to context-free grammar? So by the definition of the difference of context-free grammar, you can also generate the grammar like production rule itself, right? Now, again, these are already covered in your lectures, so do go through them. Another important topic that you definitely should revise is if you are given a regular expression, how to create NFA, like non-deterministic finite automata, or how to create DFA, which is deterministic finite automata. You should definitely revise these topics, especially because if you see the past papers, you will see that you have very similar type of questions, like you are given a regular expression, and from there you are asked to create the diagram for NFA and DFA. And these almost hold like 15% of the total score. So if you draw NFA and DFA correctly, you easily can score like that 15 from the 100, right? So I have seen that we in the past that there are many students who just either leave this question, like they don't answer it, or they do not answer it seriously, so they end up getting less score. But creating NFA and DFA is actually like one of the easiest like way to score more in your exam, right? So Soren has asked in the chat, can we use flowchart making programs? Soren, I didn't quite get your question. What do you mean by that? So when you ask that, can we use flowchart making programs? So you can, there are different ways, right? Because it's not actually on paper. One of the easiest way I would say is you just take a paper, try to draw the NFA or DFA on the paper, and then you take a picture of that and you put that in your document, like the online document where you, or the answer sheet, right? That's one of the easiest way. Then you do not have to draw the flowchart like using, let's say, PowerPoint. But uh, if you do use, let's say, PowerPoint to create a flowchart, or you can actually use, you know, in the PowerPoint, you have symbols or shapes, right? You can use the shapes to also draw the NFA or DFA, okay, from the regular expression. So you can go either way. Either you can draw on a paper, take a picture, and then put that picture in your answer sheet, or you open up PowerPoint, you use symbols and shapes to draw the NFA DFA, and then you convert that into an image and you put that in the answer sheet. You can go either way. But one thing, keep in mind, put that in the answer sheet, okay? Don't do like, okay, refer to something else and then you submit the picture separately. It just makes it difficult for me to evaluate, right? One thing I have told you earlier as well, the easier you make my job to evaluate your knowledge on this module, of course, like you will end up getting far more lenient or better score, right? But if you make it difficult for us to evaluate like your knowledge, of course, it will be difficult on our part to give you more marks, right? So be concise, be clear, and make our life more easier so that we can give you the maximum score. Okay. Now, moving on. Again, see, I have also highlighted here so that you do not forget. Please do revise and practice how to create NFA and DFA from regular expression or vice versa. If you're given, let's say, a DFA or an NFA, how you can create a regular expression from there. Okay. Again, just to jog your memory, in case you want to revise the finite state automata and regular expression, it's in unit 4, week 19 lecture. So you can access the Moodle course directly from there. Again, reason I'm stressing this because you can easily score 15 to 20% of 100% through this itself. Okay, moving on. You already know that when we have the production rules, it can be represented in different ways. One of the most popular way that you are actually taught in the module is Backus-Naur form or Backus normal form or BNF in short. So BNF is a meta-syntax notation for context-free grammars, often used to describe the syntax of programming languages, right? So if you can recall that as part of the grammar, you're given different production rules. The production rule could be something like E produces var ID or E produces numval, right? Now, if and when you are asked, okay, can you show us the Backus-Naur form, right? Then it's one of the easiest way to also score quickly. It's because all you do is change the representation. So if you are given the production rules, where you can recall that the production rules has, let's say, the non-terminal arrow, which is the produces, which means the produces, right? The arrow itself, and then a terminal or a non-terminal. So what you do, you take all the production rules for the same non-terminal and you put them side by side using pipe sign. So Backus-Naur form will look something like this, that E, right? It's one of the non-terminal. Instead of arrow, you use colon equal, and then you put each of the different production rules using this pipe sign. And that's how you represent BNF or Backus-Naur form, right? Again, this is one of the easiest way. If you're asked about this question, it's very easy to score like full marks for this. So again, please do revise this one. And as you all know, like BNF is a more compact form and can be a compact form of production rules, of representing production rules, and can be written without using special symbols. So you can also have extended Backus-Naur form or EBNF, which is represented in using different symbols. But again, like do revise this as well. But in essence, keep in mind that if you are given a set of production rules as part of grammar, then you just have to replace the arrow symbol with colon equal or just equal. But usually I would prefer you to go for colon equal, okay? Colon equal, and then you just put all the production rules using pipe signs for the same non-terminal. Does that make sense so far? Thank you, Dragos, for confirming. Thank you, Curtis. Thank you, Andre. Okay, now after, as you know, the tokenization happens as part of the compiler. The tokens are generated from the program source code. Now the tokens are processed by the parsing phase of the compiler. Now, the parsing phase is also called the syntax analysis or syntactic analysis phase of the compiler, which is the process of analyzing a string of symbols, which is a token, in the programming language, such that the output can be a parse tree. So in this phase, the parsing, so the input are the lexems from the tokenizer, which is like the lexems are basically the tokens, and the output is the parse tree of the program. Now, keep in mind, in practice, the parser may not actually produce the parse tree itself as output, but instead some other information that was generated in the process corresponding to construction of the parse tree, such as abstract syntax tree or semantic interpretation can be generated, right? But that's in practice. But in theory, always keep in mind that as part of parsing, the tokens are provided as the input, and the output is the parse tree itself. The parse tree is then further processed to generate the abstract syntax tree. Now, what is a parse tree? You should already know, but again, I'm going to jog your memory. A parse tree is a graphical representation of a derivation that filters out the order in which productions or production rules are applied to replace non-terminals. Now, each interior node of a parse tree represents the application of the production or production rule. The interior node is labeled with the non-terminal, let's call it A, in the head of the production. And the children of the node are labeled from left to right by the symbols in the body of the production by which this non-terminal A was replaced during the derivation. The leaves of the parse tree are labeled by non-terminals or terminals and reads from left to right. Now, when we talk about parse tree is actually the concrete, it's also called the concrete syntax tree. The concrete syntax tree, or CST in short, is a tree that represents the syntactic structure of a language construct according to our grammar definition. So basically, it shows that how the parser recognize the language construct. In concrete parse tree or concrete syntax tree, many of the punctuation tokens are redundant and convey no information. So elimination of left recursion or elimination of ambiguity involves the production of extra non-terminals and extra grammar productions itself. So these details should be confined to the parsing phase only. On the other hand, you also have the other type of tree, which is abstract syntax tree. So an abstract syntax tree, or AST in short, makes a clean interface between the parser and the later phases of the compiler. Why? Because the abstract syntax tree, or AST, is basically a compressed version of the concrete syntax tree or the parse tree. So the AST conveys the phrase structure of the source program with all the parsing issues resolved, but without any semantic interpretation. Now, the AST is one of the form of intermediate representation that is generated as part of the compilation process. So we can abstract out or abstract away from the concrete syntax tree by, like, in order to form the abstract syntax tree, by deleting intermediate non-branching categories and pushing infix operators up to the nearest branching parent node. So let's look at an example, right? If you are given that, okay, you have the expression 2 star or 2 multiplied by 7 plus 3. If you're given this expression, can you draw an abstract syntax tree? It's one of the easiest thing, because remember, you're going from left to right, and you have to draw the tree based on precedence, because we are using multiplication that will take higher precedence. So as you can see, the AST can be generated in this form. Now, these are already covered extensively as part of your earlier lectures. So do revise how to draw AST and CST. The reason being, again, this hold a lot of mark. You can get like almost 15 to 20% easily just by like drawing AST and CST. And as I've mentioned earlier, the Parse Tree or CST, it only has a bit more information than the AST. The information consists of the information about the node itself. Okay, like 2 is a factor, right? And star is a terminal that are being used. So these are the information that are being conveyed as part of Parse Tree or concrete syntax tree. But again, that being said, you might be asked in the question that, okay, given the expression, can you draw AST and Parse Tree? Okay, so do revise or do practice how to draw AST and CST. So this is a representative like a question that being asked in 2018, that considering the following grammar for balanced parentheses, like these two are the production rule that are provided, can you draw a Parse tree, right? The solution is like this. What you do, let's say here you are given two production rule, that B produces B within bracket followed by B. And B can also produce epsilon, which is empty string. So if your input is like this, the brackets, as you can see, the way you can generate the parse tree is from the production rule, try to simplify it. So let's say you refer B1 as your own production rule from this production rule that is given. So B1 refers to that B produces B within bracket. And you also like define another like production rule, which is B2, that refers to the epsilon rule itself. So now that you have simplified these production rule in your own way, you can use that to take the input string and then generate the parse tree accordingly, as shown here. So again, as you can see, this holds 7% marks, right? So like it's easy marks for you to get. Okay, what was epsilon rule? Epsilon rule means it produces non-empty string. So here, as you can see, that B produces epsilon, it means B can produce I said it wrong. So epsilon is empty string. Okay. So B produces empty string, which means it like just produces empty string in general. Okay. So that's the epsilon rule. So does that make sense, Andre? So do keep in mind, correction, I said it wrong. Epsilon is empty string. It's not null, but it's empty string. There's a difference between null and empty string. So when you are given that B produces or B arrow epsilon, it means that B produces empty string. Okay, that's the epsilon rule. Okay, perfect. Thank you for confirming that, Andre. Again, because this is an important topic and also very easy to score like 15 to 20% of the overall 100% of your written exam, I've also like mentioned the lecture that you should definitely look at and revise and study is Unit 5 or Week 20 lecture, and Unit 6 and Week 21 lectures. Again, I've also provided the lecture links as well. So if you have access to the slide from Moodle, just click on it and it will directly take you there. Do not miss these, like revising these topics, as these are really easy to score. So again, you will be easily get like marks just by revising these topics. Okay. Now, remember, as part of the parsing, we generate the parse tree or the abstract syntax tree, but as part of the parsing, we do not check for different form of errors that could happen. So, for example, parsing does not check that whether the variable names are the same or not, with an example which is given here. The parsing also doesn't check that whether the variable is declared in advance to assigning it or not, right? Another thing that parsing doesn't do is that the different types of variables and expression that are being used are syntactically well formed or not. So these type of error checking actually happens as part of semantic analysis. And again, so you have lexical analysis or the tokenizer as part of the compiler. Then you have the phase of the parsing phase. After the parsing phase, semantic analysis happens, where you mostly do semantic type checking or type checking itself. Okay. So the main goals of the semantic analysis is that it ensures that the program satisfies a set of additional rules regarding the use of programming construct, such as variables, objects, expressions, and statements. Now, example of semantic rules includes variables must be declared before being used, or a variable should be declared multiple times in the same scope. Or a semantic rule can also include, in an assignment statement, the variable and the assigned expression must have the same type. The semantic rule can also include the condition of an if statement, which must have a Boolean type. So when we talk about the semantic rule, it also has two specific categories, at least. So you can have semantic rule regarding types or semantic rule regarding scope. So do go through this topic, that different types and scope, what do they mean as part of semantic analysis from your lectures. Now, when we talk about the type information, like the type information classifies a program's constructs such as variables, statements, expressions, functions into different categories, and then imposes rules on their usage in terms of those specific categories with the goal of avoiding runtime errors. So you can have like example, like int a, which is a is a variable, right? And the type is the integer. So you can have different form of expression as part of your program source code, and each expression can have different like a category or different types, right? That's what type information basically does. So it does type checking to validate the rules for the expression as part of the program source code. So again, like a recap, that type checking is the validation of the set of type rules. Examples include that the type of variable must match the type from its declaration. the operands of arithmetic expressions such as plus, minus, multiplication, division must have an integer type. So you, as you all know, as part of your program, you can't perform arithmetic expression on like strings, right? Most of the languages does not allow you to do that. So depending on what the language or how the language is defined, these are some of the form of type checking that is done as part of semantic analysis of the compiler or the compilation stage. You can also have with like type checking such as the operand of the comparison expression must have integer or string type so that the resultant is always a Boolean type. Okay, so these are some of the basic type checking that happens as part of semantic analysis. So once again, why do we need the type checking phase as part of the semantic analysis? Is because type checking phase determines the type of each expression in the program, which is basically the each node in the abstract syntax tree that corresponds to an expression. So the type rules of a language define each expression's type and the types required of all expressions and sub-expressions. Now, as part of type checking, you can also have static properties or you can also have dynamic properties. Now, static properties are those that can be determined by examining the text of the program without actually executing it. For example, if you are given the expression that x equals x plus z, z equals x plus 2. So here you can easily determine what's the value of x and z, depending that you do know the uh, initial like assignment of x and z, right? So given these expression, as you can see, just by looking at the expression, you can evaluate the type or the value of the output of the expression. So this is a static property. On the other hand, you also can have dynamic property. Now, dynamic property are of those types that can only be determined by considering all the possible execution of the program. Now, what does it mean? Let's say if you are given the expression that x equals x divided by z and x equals y minus 2, right? Here, you are not sure what might be the output or what might be the type of the x itself because it is dependent. So evaluation of this expression x equals x by z is actually dependent on the value of z. So if z is, let's say, integer, which is non-zero, right? Then you will have a floating point valuation of x. But what if z is 0? Then the program will trigger an error, right? Because x by 0, like x divided by 0, is definitely like it's in mathematical sense, it's kind of infinite, right? Or undefined. So in programming sense, you will get an error. So as you can see, this is an example that until unless you know the value of z, you cannot determine the type of x or the value of x itself. So in this sense, it is a dynamic property. Now, like a very common question or knowledge that you are being tested as part of the module is what is the difference between dynamic and static properties, right? So in essence, sometimes you need to keep in mind that the border or the differences between dynamic and static properties is a bit vague. Especially, let's say if you are given the example that if x equals 1e minus 2, so here you can deduce the value or type of x either statically or dynamically as well. So in some cases, you need to keep in mind that we can conservatively deduce apparently dynamic properties using static techniques as well, by using symbolic execution. Now, symbolic execution is a means of analyzing a program to determine what input causes each part of the program to execute. And also do remember that for your exam, like do learn the differences between dynamic and static properties or static typing, okay? Another important concept that you should revise is the dynamic tree or dynamic syntax tree. So DST, in short, is an alternative to abstract syntax tree and parse tree. Unlike the statically typed programming languages, the analysis of a dynamic programming language has to estimate the type system, such as the types, variables, functions, from the code fragments semantics, as well as it also has to determine the configuration files and the binary files, right? So in dynamic programming language, estimating the type system for all these different forms is actually represented using dynamic tree or DST in short. So dynamic syntax tree implementation also takes into account non-static and non-typed implicit and explicit declaration so that the resulting information covers most of readable dynamic code fragments. Now, that being said, do revise the pros and cons of AST, CST, and DST, especially related to issues related to compile time errors. Okay. Another important topic that you were taught as part of the compilation process is how to deduce types or type deduction and based on an environment. So we often express our logical steps, that is the deduction rules, within the context of an environment. Environment in this sense is basically the computing system. So we represent the environment as the capital gamma sign. So the gamma environment is the context in which the variables are declared, which basically means that within the environment, that is within the program, these rules governs, then a series of rules will be presented that are applicable in the context at hand. Now, what is it meant? What does this mean, right? So the environment or the program, computing program, is represented using this gamma symbol. So you might be given that, okay, what if you are given the gamma symbol types such as this, like these are the type rules, such that the environment can have integer, environment can also have int v, which is a variable that is of a type integer itself. And then you are also given, okay, given the environment of the program accepts E1 and E2, which are also of integer type. So you can perform E1 plus E2, which itself is also an integer type as well. Another rule is you might be given that integer E1, which is an integer, and E2, which is an integer. If you perform E1 minus E2, then the type is again an integer as well. So given for an environment, if these type rules are provided to you, you might be asked, okay, can you then specify what will be the type of the expression, which is a plus 3 minus b. So what you need to do, again, if you go through the previous lecture on this, you will be able to see that given the expression, you can actually use these rules that are provided, type rules that are provided, to deduce the type of the whole expression itself. And that can be done by like this. So as you can see, you like have the full expression, which is a plus 3 minus b, but you start by breaking it to different part of the expression and deducing each type. So as you can see here, we have the rule a, b, c, d, right? So what you do, you know from a plus 3 minus b, you have the first part, which is the variable a. So that falls within the rule b, which is here. And from rule b, you know it is a type of integer. Then the second part, which is 3, right, as part of the expression, which is a type of integer depending on the rule a, which is provided. And you go on like this till you finally deduce the type of the expression, which is basically int, because it conforms the type rule provided in D. Okay, here. Now, why this is important? Again, in the exam, you might be given a similar scenario where you are given set of type rules and you are asked, okay, can you deduce the type of the expression? Then the expression is provided to you. So do practice this topic as well, and practice other similar question from previous year's question papers, so that you are confident that you can deduce the type information. Again, this is a very easy to gain marks or to gain score as part of your whole exam. So please don't forget to revise this topic. And as you all know, so from the abstract syntax tree, right, which is a form of intermediate language representation or intermediate representation, which is part of the backend compiler process. Now the intermediate representation is further processed in the backend by the optimization phase to produce the optimized intermediate representation. So going back a bit, like taking a step back. So from the Parse tree or ACE tree, we could produce the machine language directly. However, it is often convenient to first generate some kind or some form of intermediate language representation, or IL or IR, which is basically a high-level machine language for a virtual machine. Again, as you already know, it's also called intermediate representation, or IR. Now, from the high-level intermediate representation or high-level machine code, a low-level intermediate representation is generated. Now, low-level representation is essentially an instruction set for an abstract machine. Now, alternatively, for low-level IR, like you can also have tree address code, or you can also have tree representation, and you can also have stack machine. So do revise these topics, especially example of each of these ones. Okay, you might be asked something related to this in the exam to evaluate your knowledge on like intermediate representation itself as part of the compilers. Now, as I've already mentioned, like when we discuss about intermediate representation, it's actually a high level machine code for virtual machine. So as part of virtual machine, you have also learned the concept of stack machine. So let's recap a bit on that. A stack machine is a mode of computation where executable control is maintained wholly through the append or push operation, read off, and truncation or pop operation of a first in, last out uh, memory buffer, which is called a stack. Now, this stack machine requires very few processors registers. A simple evaluation model consists of, instead of registers, a stack of value for intermediate results are used. Now, example of stack machines is like Java virtual machine itself, right? So keep in mind that each of the operation as part of stack machine consists of, it pops its operation from the stack of the top of the stack. It then computes the required operation on them and then pushes the result onto the stack again. Okay, so do revise the like topic of stack machine as virtual machine and related relevant topics to this. That being said, let's say you might also be asked, okay, if you have a program to compute 7 plus 5, can you like show step by step to perform a stack operation on stack machine? So in that sense, your answer or your result should be something like this. You do push 7, where you push the constant 7 on the stack. Then you push 5, where you push the constant 5 on the stack, and then you perform the add operation, which is like pop 2, 5, and 7 from the stack, add, and then push the result, right? So you might be asked to perform something similar as part of your exam as well. So do revise the topic of stack, machine, and also, that being said, do revise how to perform tree address code generation if you are given certain program or certain expression. Now, advantages of stack-based intermediate language, right? Do kind of go through this as well, which consists of uniform compilation schemes, or it can lead to uniform compilation scheme. Hence, the compiler is simple in nature. The location of the operands in stack-based intermediate representation is implicit. And that means no need to specify the location of the resultant as well in such a machine. You can also have fewer explicit operands in the instructions, which means smaller encoding of instructions and more compact programs. So do go through these advantages and disadvantages of stack-based intermediate representation or intermediate language from your previous lectures, because this is also an important topic for your exam. Now, that being said, another very important topic that you need to study or revise, which you have already learned in the previous lecture of the module, is liveliness analysis. So in essence, the liveliness analysis, using that, you try to see if a variable is live within a scope or not. So again, a variable is live if it holds a value that may be needed in the future for execution purposes. Okay. Now, how to calculate liveliness? That's also a very important part as part of your exam and also as part of the module as well. So a variable is live on the edge if is direct path from that edge to a usage of the variable that does not go through any definition. So you can also have live in and live out. Now, this is the theory, right? But given the theory, in the exam or in practice, you might be asked, okay, can you determine whether a variable is live within a certain scope of the program or not? And let's take an example on that, right? So you might be given a program like this, where you have like A leads to 0, B leads to A plus 1, and so on. So here you might be asked, can you check which like of the variable is live at which stages of the program? The way you do that, break the program, each expression of the program or each line of the program into a control flow. After you have broken the control flow, from there, it will make it easier for you to determine whether the value of a certain variable such as A, B, C is live within that control flow or not. So do practice the like how to perform liveliness analysis using this technique as part of your exam preparation or revision as well. Now, like these were the main topics of the module that you should definitely revise or study as part of your final exam. So just to summarize all these stages stages of compilation or compiler. So first you have the lexical analysis, which recognize the word, and generally it's a bit trivial because as part of the lexical analysis, you create tokens, which is then further processed in the parsing phase. Now in the parsing phase, it identifies the sentence or the input and then produces the syntax tree. Now, after the syntax tree is generated, it is then further processed by the static semantic analysis of the compiler. So once parsed, we can then check. When the parse tree is generated, so that means it is being parsed. We, as part of the compilation process, we can then check whether the program is meaningful or not. So full analysis of meaning can be complex, but again, as part of the compiler, it's like very important to do that or to perform that. So compilers perform conservative analysis to check for consistencies, such as type checking or items defined before like they're being used. So this is all part of the semantic analysis phase of the compiler. Now, after semantic analysis is done, the annotated abstract syntax tree is then further processed by the optimization phase. So in the optimization phase, you have like, it makes the program more efficient, which means it is smaller in size and it's faster to execute on the targeted computing machine. So the way it does that is by removing any redundancy from the abstract syntax tree or the intermediate representation that is generated from the previous stage of the compiler. Now, after the optimization is done, code generation happens, which basically like it translates the intermediate representation into machine code. And then like the translation, it's very similar to the different like human language that happens. So let's say if I am a native speaker of English and I meet someone from Spain who speaks who is a native speaker of Spanish. So if I want to communicate something I need to translate English to Spanish, right? It's very similar what happens in code generation. So from the AST, like we convert that to intermediate representation. The intermediate representation is further processed to generate low-level intermediate representation. And from there, the like executable code is generated for a particular targeted computing system on which the program source code was initially meant to be executed. Now, that being said, we have actually covered the whole module and the revision topics in almost one hour, a bit over 1 hour. But again, I would like to say all the very best for your exam. Now, do go through the topics that I have mentioned as part of this revision lecture or revision session. I will put this revision session very quickly, like on the Moodle under the revision section. Okay, so you can on your own time and at your convenience go through this once again and revise accordingly. So that being said, do you have any questions? Any more questions? Okay, thank you so much, Andre. And I really appreciate, like, you have been a brilliant class this year. And again, all the very best for your exam. So before I end this revision session, do you have any more questions for me? Thank you, Curtis, for confirming. What happens next week? Nothing happens next week. On my calendar, there is no revision lecture or anything for next week. Do you guys have anything scheduled for next week? Okay, somehow I'm not sure why it's not on my calendar, but if can someone confirm what is the time so that I can check with the scheduling office, like of school office, that why it's not showing up on my calendar? Can you confirm when is the next week's lecture? But that being said, 1 p.m. on Tuesday, right? Okay. Let me take a note of this, okay? Yeah. So thank you for sharing this. I will double check. On my calendar, it's not showing, but I will come for the lecture again. So in the meantime, if you have any question that you would like to ask, or any specific thing you like want to kind of demystify or clarify, just let me know and I will be like, I will help you out. Okay? Does that make sense then? Okay. Thank you so much, everyone, for today's revision lecture. And once again, all the best with your preparation and revision. I'm not trying to put pressure on you, but I do expect you to perform well. Because again, today as well, I have basically given you the roadmap to score the most in your lecture. Now everything is on your own hand and how you revise for the exam and how you perform during the exam. Do not be nervous when you give the exam. Just keep your head calm and cool and try to answer as much as possible. Okay. Once again, all the best, and we will I will see you hopefully in the next revision lecture. If not, all the best. Give your best. Okay.